In a previous video, we demonstrated a sensor with a CMOS latch that can be activated once it's in place with limited access, as represented by an ice cube, maybe a medical or industrial device. Here's the latch reference circuit. This is great for single-use electronics, but you can't easily turn it off once it's activated. A more flexible solution is to magnetically activate a microprocessor with a hardware interrupt. We used a modified Trinket ATtiny85 evaluation board, since it has a bootloader and can be easily programmed with an Arduino IDE. We removed the voltage regulator and disconnected the power LED to reduce the quiescent current. We also decreased the LED current. The sensor is connected to the microprocessor's priority interrupt. We can power it with a 3-volt button cell. We used an ADL1 series GMR switch sensor, which is our lowest power 3-volt sensor. It's internally duty cycled to reduce power. Let's test a breakout board. The supply current is shown on the meter on the left. They're specified for a maximum of 0.16 microamps at 3 volts. That's negligible compared to most microprocessors. The meter on the right shows the resistance of the output. The switch closes at just 1 millitesla, so it's sensitive to a magnet several inches away. Here's the microprocessor sensor assembly. This is our smallest switch sensor at 0.65 millimeters square. The microprocessor boots into sleep mode. The quiescent current is less than 20 microamps, so the battery will last a long time until the circuit is activated. Many microprocessors are even lower power. The sensor generates an interrupt to wake the processor and turn on an LED. If we activate the sensor again, the processor goes back to sleep. To show we can activate it with no access, we put the assembly in a jar, put the jar in a glass, weight it down, and add water. It can sit this way for a long time since the sensor is such low power. It still works. The battery wasn't depleted, and we can activate the processor. Here's the program we used. The setup section turns off non-essential functions and slows the master clock to reduce active power consumption. The sensor goes low when activated, so we attached a low-true, high-priority hardware interrupt. The program loop puts the microprocessor into a power-down sleep mode and stops here to await an interrupt. We used 4 loops for delays since the timers were deactivated to save power. In the active mode, the processor monitors the sensor and powers down if the sensor trips. Here are the parts we used. These sensors are ultra-low power and ultra-miniature, with 3 options for the activation field. Contact NVE or visit nve.com for more information.